Hello everyone. Once again, welcome back to Code the Brain. Last week, we built a single layer perceptron and trained it to learn the AND gate. But we didn't see how the network actually learns. Today, we will discover the secret sauce of neural networks. In this today's video, we will be learning about loss functions, then we will be learning about gradient descent, which helps us to how we decide which way to adjust, and finally we will be discussing about backpropagation. So what is backpropagation? Backpropagation is how we update all the weights efficiently. And finally, we will code a two-layer neural network that learns the XOR problem, something a single neuron can't do. So, now let's cover our first part, our loss function. How does a network know it's wrong? And the answer is using a loss function, also called a cost or our error function. So, suppose our prediction is assume 0.8 and the target was, let's assume our target was 1. So one simple loss function is mean squared error. Now if I write it down, it is something like the mean squared error is 1 over n of n I till 1, and finally yi minus yi cap square. So where our yi is our true level and our yi cap is our prediction. So now the higher this number, the worse the prediction. In classification, we often use other functions like cross entropy. But today we will stick to mean squared error for our simplicity. Now let's cover our second part, or our gradient descent. So once we know our loss, the next step is to fix it. Change the weights to reduce the loss. But how do we know which way to move the weights? That's where gradients come in. The gradient tells us if we change the weights a tiny bit, how will the loss change? Then we update the weight like this. If I write down the equation for this, our w will be minus eta multiplied, oh my god, dl over dw. So here our eta is the learning rate. Let's say our eta can be for example positive 0.1 or anything, and our delta L over dl over dw ddl of dw is the gradient. Think of it like going to downhill. The gradient tells us the slope, and the learning rate tells us how big a step we take. If the slope is steep, it means it is a big correction. If the slope is flat, it means a small correction. Over many steps, we get closer to the bottom, which means lower loss. Now, our final concepts or the backpropagation. If we discuss about backpropagation here, let me write it another color. Yeah, not this one. Let's see. Okay, if we write about our backpropagation, so for our backpropagation in a multiple layer network, the tricky part is the output depends on many weights. So how do we compute the gradients for every single weight in hidden layers? The answer is the legendary backpropagation algorithm. It uses the chain rule from calculus to efficiently compute how each weight contributed to the final error. Here's the big idea. Do a forward pass or the compute prediction, then we compute the loss, then do a backward pass. So start from the output layer, start from our output layer to compute our gradient, then we pass the gradients backwards to the hidden layers. We pass it to the hidden layers, and then what we do is we update all weights and biases. This way we efficiently train even deep networks. Now comes our final part or the coding part. Now at first let me just, we're using Google Colab for this. At first let me connect my Google Colab, and usually we use NumPy, port NumPy as NP. Then we will create the 4 samples or do the dot random dot seed of 42. Then what we do is we will create the XOR data. So for the XOR data set, np dot array here we will be creating our 0 0, then comes our 0 1, then comes our 1 0, and finally we conclude with our 1 1. Now we write our predictable datas, our y here np dot array, then our third braces, and finally our outputs here 0 1 1, and finally a 0. So this is how we created. We have 4 samples, the truth table of XOR. Now we initialize our weights and biases. Now we do the input let's say dims here. Let's say our input dim as 2, our hidden dimensions will be also 2, and our output dimension will be 1. Okay, now we write our weight. At first, our weight 1 here. For this, we write np dot random dot rand n, and then we pass our input dim and our hidden dimension. And for bias 1, np dot zeros 1, and hidden dimension np dot random hidden dimension, output dimension 1, and output dimension. Yeah, to get this, you can get this from your settings. From AI assistant, it will show you the the inline completions if you're stuck with something, or it will give you some suggestions. Okay, so here our 2 neurons in the hidden layer and 1 is in the output layer. Now we write our output function. At first, let us run this thing, both of this. Yeah, okay, now we write our activation function, or our sigmoid function. Our sigmoid function here, x, here we will be returning our 1 over 1 of plus np dot exponential of negative x, and now we do the define the sigmoid derivative here, derivative of return x over sigmoid of, we return the sigmoid of x, sigmoid of x, sigmoid of x, yeah, sigmoid of x multiplied 1 minus sigmoid of x. Yeah, that's cool. Now we write our training loop. Here we will be using our learning rate in let's say 0.1, and we will be using 10,000 epochs. 10,000 epochs. Now we write our loop for epochs in range of epochs. We will be doing at first our forward pass, or z1. Here we will be doing our np dot of our x and our weight 1, and we will be adding our bias 1. Now we do our activation 1, sigmoid of our z1. Okay, now we do for the z2 of np dot of a1 comma w2 plus our b2, and then we do our activation of this sigmoid of a z2. Yeah, now what we do is we compute the loss. To compute the loss, we will be defining another variable here, np dot mean and then we do is y minus a2 square. Now we will be doing our backward pass. To do the backward pass, we simply write dz1 of, here we will be doing at first, if we do at first, let's do the dz2 cause it will be using in dz1. So at first, if we do the dz2, here our a2 minus minus y, and dw2 will be np dot a1 dot t of dz2, and np dot sum of dz2 axis will be 0 and keep times true. Yeah, now we will be doing our for our dz1. If we do the dz1 here, if we do the dz1 here, we will be doing our np dot of our dz2 w2 of transpose multiplied sigmoid of derivative of z1, and then we np dot, yeah, this looks great. Okay, now we update our values. W2 minus equal will be learning rate multiplied with our dw2. It is a small one, yeah. And now we update our bias true will be our LR multiplied with our db2. Now same goes for our w1, minus 1 will be our LR multiplied with dw1, and finally our b1 is minus equal learning rate multiplied with db1. Now we check for losses. If let's say epoch, yeah, this looks good. Now here, for every loop in the forward, it gets the prediction in this part, then in the backward it compute the gradients, and finally here we update the loop. After 10,000 epochs, the network usually learns the XOR. Now let us run this. Yeah, here you can see. Okay, so now let's test this thing. We print our trained XOR results here for I in range of length of x we used capital X, so yeah, that is why it is giving an error. Okay, so yeah, okay, now we do our prediction here. Pred of sigmoid of np dot sigmoid np dot of x of I w1 plus b1, and then w2 and b2. Now once we, let me close this. Yeah, I hope this will work. Okay, let's check. Yeah, here you can see our trained XOR results. So our prediction should be close to 0 or 1, as you can see here, solving a XOR. Now we recap our today's topics. So what we learned today? Today we learned about neural networks. We learned about neural networks. By minimizing loss, we learned about gradient descent, which tells us how to change weights. We learned about backpropagation, which helped us to efficiently compute gradients even in multi-layer networks. And finally, we built a two-layer of neural net from scratch to learn XOR. Next week in Coding Brain, we will go deeper. We will build a multi-layer network. We will be exploring activation choices like we will be using ReLU and 10H, and see why deeper networks can model more complex data. Drop your questions in the comments and see you in week 3. Thank you so much. Hit the like and subscribe for more contents.